Hi, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln. Now I've done quite a few videos kind of on planets and on galaxies, but this time around I want to go a little bit further than the galaxies and look at dark matter halos. And these are these enormous structures that kind of surround galaxies, and they play an important role in their formation and their evolution and things like that. And this particular one, I want to have a look at dark matter subhalos. This is kind of like going to be smaller halos located within the main dark matter halo around galaxies. So just to recap, really, this is going to concern galaxies and the dark matter halos around those. So galaxies are enormous systems of stars, gas, dust, and also dark matter, and these are held together by gravity. So a disk-like galaxy like the one here, a spiral galaxy, will be rotating like a disk, and an elliptical galaxy will be more spherical. But basically we can't see the dark matter, but we can infer that it's there basically through its gravitational interaction. Now, different sorts of galaxies have different amounts of stars, gas, dust, dark matter in them. They're not all kind of have the same ratios there. So they all come in different sizes as well. Sizes, shapes, there's a whole variety of different sorts of ones. I've done lots of videos on the different sorts. So you have like spiral galaxies, elliptical galaxies, irregular galaxies, even jellyfish galaxies, ones that are kind of distorted, spherical, so a whole range of different sizes and shapes. But the one common thing that most appear to have is these dark matter halos and their general composition in general. So, observations of these galaxies kind of suggest that they're surrounded by these dark matter halos. These are kind of these large spherical structures and extend well beyond the visible part of the galaxy. So if we actually look at a galaxy, take an image, then we're not actually looking at the dark matter part. We can't see that because it doesn't emit anything that we can actually detect, but we can detect it from its gravitational interaction. And this dark matter halo goes well beyond the visible part. So, maybe an order of magnitude greater than the actual outer edge of the visible part of the galaxy. So these can be enormous structures around the outside of it. So it doesn't really emit anything that we can measure. They're not easy to detect, so they're not visible, but it does interact gravitationally. So whilst we can't actually see it, it is having an effect on the matter in the galaxy and all the surrounding stuff as well. So it's only interacting through gravity. Now, galaxy clusters also have dark matter halos on much larger scales. So these clusters are essentially groups of galaxies in a higher density kind of region of the universe. And these also have dark matter halos, and they play an important role again in the formation of those clusters and then the formation of those galaxies within those clusters as well. Now, again, we can't see them in a galaxy cluster, but we can essentially measure the gravitational interaction of the dark matter through things like gravitational lensing. So you've got a galaxy cluster here, and you can see these kind of arcs, and they're caused by gravitational lensing, and that's because these galaxy clusters have enormous amounts of mass in them, and not all of the mass we can actually see. So this would be dark matter. So again, by looking at the distortion of the light as it passes through these galaxy clusters, we can actually calculate how much dark matter is there and also how it's distributed as well. But for a single galaxy, we have to use things like kind of rotation curves or the dynamics of the galaxy, really, because that is impacted by gravitational interactions from the dark matter, essentially. So a disk-like galaxy like the spiral galaxy of the Milky Way, we would expect that the orbital velocity, so it's rotating like a disk, as you got further out from the centre, that it would get slower. Think about the planets in the solar system. The ones further out are orbiting slower than those closer in. And we call that kind of motion or law, I suppose, Keplerian. So we expect the drop off. That's what we predict. As we get further away from the centre of the galaxy, that they should be orbiting slower. So that rotation curve should decrease as we get further away. However, when we actually measure the rotation of pretty much all these galaxies, it's flat. It doesn't decrease with distance. It stays relatively flat, which means that the velocity is too high. They're rotating too fast on the outer parts of the galaxy, and that's not predicted. And really kind of the only way that can happen to kind of fill that gap, to increase the velocity, is to have some mass there, have a halo of mass that we can't see. And this is kind of where the dark matter halos come from. And again, we can't see it, but we can essentially model how to get that rotation curve flat by distributing mass and matter around it that we can't see. And it basically gives us this kind of like spherical structure. Now, you might assume that it's kind of like smoothly distributed, but it's not. So if you kind of zoom out and look at it broadly, then the surface mass density kind of might decrease as you get further out. This is the dark matter halo anyway, but it's not smooth. It's going to be bumpy, and there will be local kind of clumps within that, or voids as well. So it's not completely smooth the way that dark matter is distributed in this halo. In fact, it's actually populated by these smaller dark matter subhalos. So these are smaller halos of dark matter located within the larger dark matter halo, and these are kind of gravitationally bound to the larger dark matter halo. So you've got these kind of smaller ones within the much larger one, and these are known as dark matter subhalos. Now the interesting thing here is, again, we can't see those. They're not really visible directly. However, quite a lot of these dark matter subhalos are often associated with satellite galaxies. So let's take the Milky Way, a spiral galaxy. We have lots of smaller dwarf galaxies that are orbiting around the outside of it. They're known as satellite galaxies. Now, many of these dark matter subhalos are actually kind of halos around these smaller satellite dwarf galaxies. So they kind of be associated there on a much smaller scale. Now, they're not all associated with these satellite galaxies. If they're not, then they will be invisible or dark, and then we actually won't be able to directly see them. But nonetheless, these dark matter subhalos, as well as the dark matter halo itself, they're very important for understanding how galaxies form and how they evolve. We know it impacts the rotation curves of galaxies. We also suspect that it's going to impact how they form, how they get to be like they are in the present universe, how fast they form, how they merge and evolve into different sorts of galaxies. So understanding where they are, their distribution, their density, their size and shape is all important for understanding how the galaxies themselves actually form. So thank you for watching. If you enjoy the video and find them useful, then do consider becoming a member of the channel. There's extra videos in the member section.